got one other spherical coordinate that's allowed to vary. So our generalized coordinate in this case, because there is one degree of freedom, there's one generalized coordinate. And that's theta. Okay. Now we go to step 3, transformation equations. We've got to now write x, y, and z in terms of theta. Anybody know how we're going to do that? We're going to use spherical coordinates, right? I mean, you've got spherical coordinates. That's the way we set this up. So we're going to say x is equal to rho, and rho is a sine theta cos phi, but phi is omega t. Y is rho, which is a sine theta sine phi, which is omega t. And z is equal to rho, which is a cos. Right, so those are our transformation equations. Now we have to write out the kinetic energy. This term turns out to be a bit of a hassle to write down. Remember that we can do that now. We've got three steps like that, three-dimensional system. And we have to convert that into spherical coordinates. Now one way of doing that is to take each of x, y, and z, differentiate them one by one, and to work out then the sum of the squares of the components. There's another way. I'm not going to tell you what the other way is now, so let's do it this way. It's important that we understand as much and as many different ways of doing things as possible, because in pretty good problems, different problems that I come up with or that you come across when you're doing an assignment, different techniques will work. Some things won't work, some things will work. So let's follow this through, right? This technique generally always works when we know normal particles are in the system. It can be a bit tedious, but let's work it out. So the first thing we do is we work out x dot. X dot is, well, A is not time dependent. So I don't differentiate it. Theta is time dependent. So A theta dot cos theta cos omega t, and now minus A omega sine theta sine omega t. Y dot can similarly be written. Anybody want to tell me what it is? First term here is going to look like, I'm differentiating with respect to theta first, and then with respect to time. So it will be a dot plus theta sine omega t omega theta. Right, that's correct. And z dot, in this case we only have one time dependent thing, so it's quite easy. Simply equal to minus a theta dot sine theta. Right, so square each of these terms and add them together. What do you get? Oh, that's a nice little exercise for you to check. I'm just going to write down what I believe to be the answer. Half m, and I think it looks like a squared theta dot squared plus a squared sine squared theta phi dot squared is only right, you can check that that is indeed what we get. And we add all those squared. Like I said, there's another way in instances we might come across later. When you're adding and squaring, and you can of course be clever, when you add these two together, you can realize that the cross terms cancel. You just have to add each one. There's a cos and a sine, and a sine and cos. And so this is just going to look like a squared theta dot squared cos squared theta. And this one's going to just look like a squared omega squared sine squared theta. So this one is a squared theta dot squared sine squared theta. These will then all add up. This term and the other one. So yeah, and you can kind of solve it if you're not going to write anything down. So we've now got step 4 done. So we move on to step 5, generalized components of force. And this is the first time that we're going to see this done in any real extent, because previously we were just kind of rewriting something that was obvious. What force is acting on the bead? What forces are acting on the bead? Right here, normal force, gravity. Normal force is what kind of force? So what do we do with forces of constraint? We ignore them. They're not worthy of our time. We went through a whole lot of effort getting Lagrange equations to work for precisely this reason, so that we can simply ignore the forces of constraint, pretend they're not there. That's why we have generalized coordinates. That's why we change into a coordinate system that only parameterizes the constraint magnitude. So we ignore the forces of constraint. We only have one force of interest to us, and that is gravity. Right. So the force of interest to us is gravity. In the way we parameterize everything, the way we set things up, gravity is minus mgz. It's going downwards, and its value is mg. So we know what gravity is. Let's get generalized component of gravity in generalized coordinate direction theta. We're only going to get one generalized component of force because we only have one generalized coordinate, one degree of freedom. Previously we had two, now we have one. So let's get q theta. Right. And there's a lot of ways of doing this. The way we've been doing it so far is we've already been writing theta dot f. That's the same when you think about what this really means as writing del x by del theta fx plus del y by del theta fy plus del z del theta z. That's what that is. We write it out, we expand this, we get this. And this is generally kind of, you can go directly from here to here when you get comfortable with the notation. What's fx, the x component of the force? And this is force moves in the z direction, so what's the x component? What's the y component of the force? 0. What's the z component of the force? Minus mg. So this is equal to del z by del theta times minus. What's del z by del theta? Well, we can look at the transformation equation to figure that out. The transformation equation says z is a cos theta. If I differentiate it with respect to theta, I'll get minus a sine theta. Minus is cancelled, and that just looks like mg sine theta. Okay, so I've got my generalized component force, and there's now time to compute and to write down Lagrange's equation. Writing down Lagrange's equation, it always looks the same. Step 6 is going to be very similar. It's just a matter of writing it down to our particular generalized coordinate. In this case, theta. So we're going to write q theta plus del t by del theta is equal to d by dt del t by del theta. Alright, and now step 7. Let's substitute everything that we have worked out into this equation and get our equation of motion. And you can see we're going through an algorithmic procedure. So q theta, here it is. mga sine theta, del t by del theta. Is there a direct theta dependence in t? Yes, there it is. So when we differentiate t with respect to theta, what do we get? Well, the 2 comes down, we sine theta cos theta, so it looks like m omega squared a squared sine theta cos theta. Alright, what about, we don't skip steps. What about theta dot? Is theta dot dependence in t? Yes. There it is. When we differentiate, what do we get? 2 comes down, ma squared theta dot. Right. So we can differentiate this. And I said don't skip steps, so we will differentiate on the next step. Ma squared theta double dot. In this case, a is independent of time, m is independent of time, so we can differentiate just the theta term. And this is equal to mga sine theta plus m. Okay, let's rewrite this term. We've got a sine theta cos theta here. That looks like something, a double angle formula. Sine 2 theta, right? Except there should be a half inside because sine 2 theta is 2 sine theta cos theta. This looks like a half m omega squared a squared sine 2 theta. Right, so we've got an equation. We can divide by this. We want to see how theta moves. We want to get a different equation of theta. That's what we use in the lab. So we can divide by the stuff in the front, ma squared, everywhere. And what happens? Divide by ma squared here. We can divide by it here. And we can divide by it here. So we have 1a there. And that is the equation of motion. That equation of motion tells us how theta moves as a function of time. We know there's 2 terms in this equation of motion. This term, this term. Now, if we think intuitively about the next group, the beads about then we imagine that if we did not spin the loop, if we just let the bead drop, it would oscillate around the bottom. It would pursue the exact same motion as a pendulum. And that's term 1. That's what term 1 is giving us. It's telling us this motion that is similar to the motion of a pendulum. Term 2 is a different term. As I spin the loop faster and faster and faster, and as I increase omega, there's a new tendency. If you think about the system, as I spin the loop faster and faster, the bead is going to tend to move towards the side of the loop. It's going to be pushed outwards by a centrifugal force, if you like, on the bead. And if you were, in fact, analyzing the physical equations, you would, in fact, use the centrifugal force to get this term. But it comes out for free when we use the Lagrange approach. And as we increase omega, this term into play, and this term, you should convince yourself, pushes the bead towards the side of the loop. You should convince yourself by asking yourself, where is sine 2 theta big, and where is sine 2 theta small? Where is sine theta big, and where is sine theta small? What does this mean about where the bead is being pushed? Right, it was an oral test question already. At some point I will submit the answers to these oral tests. I have been employing the notion that I should send the person with the top mark an email asking them if they wouldn't mind writing up their answers, and so that I can submit for the rest of the class. But I've only done that once because I only marked one. Second one I've marked, but I haven't yet written down the person. And we have got one oral test ready to be uploaded. I'll upload it probably after today. And then you'll see what these things are like if you haven't done one yet. Right, so that's the procedure. Very algorithmic, very simple, it's very easy. We always do the same steps. We choose the degrees of freedom, we choose the generalized coordinates, we write down transformation equations, we work out the kinetic energy, we work out the generalized force, we write out our Lagrange equations, we substitute everything, turn the handle, and the equations of motion come out. Right, so we can now see that Lagrange equations certainly are a algorithmic step-by-step procedure. And that's another advantage of the Newton's equations. That they in fact enable us to work things out with a lot of ease. Now, we've looked at a couple of applications. So what I'm going to do is I'm going to carry on this tour around town and start visiting some of the slight deviations that we might make to the Lagrange equations. By the way, you can now, I think, do up to tutorial 8 in the chat book. If you have any problems with the class, at this stage, you can yes, tutorial 8 is what we have for today. Probably tutorial 9 as well, after today's. So, up to tutorial 9 certainly isn't available. We'll talk about some of these concepts on Thursday during the touch. But you should look at them. You should kind of familiarize yourself with them. Make sure that they're not foreign. Okay, so. What we're going to look at now is we're going to look at what happens when all our forces in the system are conserved. Right. And we may have time today, although most likely we'll actually get around to Wednesday, to really question what it means. What conservative means? What other things imply conservative? For now, let's just write conservative means that I can write my force as the gradient, negative gradient of some potential energy. Right? So we'll talk about this. We'll talk about different ways of seeing that something is conservative. We'll talk about Stone's theorem and all those little pieces of mathematics. But for now, let's just take it for granted that our forces are conservative under this definition. What does that mean for Lagrange's equations, Lagrange's equations? Well, let's write down Lagrange's equations and let's try and figure out what this does to them. I'm going to assume also, and this is important, that u is a function of x1 to xn. It's not a function of time, it's not a function of velocity, only of position. That's pivotal, right? There are other formulations of Lagrange's equations, mechanics, and other formulations of physics in which I can change this as monogenic physics or whatever. But we're talking about conservative, and u is a function only of position. The first thing I want to do is I want to ask, what does this equation mean? Let me unpack it. So it means that the x component of the force is minus W by Δx. Means that the y component of the force is minus W by Dy. And it means that the z component of the force is minus W z. Write out the vector equation. That's what it gives me. But remember that when we're working in Lagrange equations, when we're working in this course, essentially, we're not entirely satisfied. To have an equation terms of x, y, z. We've been going through quite a lot of effort to get away from thinking about things in terms of x, y, and z, to move into thinking about things in terms of these so-called generalized coordinates. And so instead of thinking about this equation as x, y, and z components, I would like to determine a generalized component of force in some direction associated with generalized coordinates. So remember that qi, right, the I generalized component of force can be written as EI dot F. And just now we saw that, EI is just del by del QI, remember? Del position by del QI. So we saw that this can actually be written as a sum, the J maybe. In fact, I'm not going to write it in this funny term. I'm going to write it one step by step. So it can be written as del x1 by del QI times F1 plus del x2 by del QI F2 plus, right? Because F is F1, F2, F3, and EI is del x1 by del QI, del x2 by del QI, and so on and so forth. So I'm just really writing out the vector dot product. Del xn, del QI, and n, right? So that's an equation for generalized component of force. Let's write this out in terms of what F1 is, what F2 is, and what Fn is, right? So we had F1 or Fx is minus del u by del x, minus del u by del x1. F2 or Fy is minus del u by del y, minus del u by del x2. And F3 or Fz is minus del u by del z, which is minus del u by del x. So we can write this out. This is del x1 by del qi. Let's put a minus. It's going to come. F1 is minus del u by del x1. We're going to have another minus del x2 by del qi, del u by del x2 minus del xn by del qi, del u by del xn. Right, those of you who are familiar with the chain rule will be pointing out this, and this. Right, so this looks like a multivariable chain. Okay, it is a multivariable chain. I'll write it out in sum notation. Some of you have seen the chain rule only in sum notation, so I'll write it out. I'll stop the order of these terms as well. Sum over j, del u by del xj, del xj by del u. That's what we have, right? Now we know that when we have this, u is only a function of the xj, then this is nothing other than del u by del q. So when we have a conservative force, when the force we're dealing with is conservative and there's some potential energy associated with that force, a very interesting thing happens. Whether we're dealing in Cartesian coordinates, fx is minus w by del x, fy is minus w by del y, z is minus w by del z, or whether we're in fact dealing in generalized coordinates, the expression is the same. qi is minus del u by del qi. So in fact, once we've got a potential energy, there's something inherent, something special about our expression of the force, the ith component of force, or the ith indeed generalized component of force in our generalized coordinates in terms of that potential energy. Let's make use of this now. Let's use this to rewrite Lagrange equation for motion for the case when all forces are conservative. We'll be talking about which forces are conservative in more detail as we go along. In fact, in a sense, all forces are consistent. But it's only a very deep level. And there are things that we deal with that we aggregate and where we ignore half the system, like friction, where we cannot say. At a very deep and fundamental level in physics, when we drill down and we consider everything and we bookkeep everything and we account for sound being emitted and every bit of energy being let off, heat, sound, everything, electromagnetic waves, then we can start talking about everything in physics. But when we ignore half the system, it's not good. Right, we'll deal with that in a minute. But let's look at what the Lagrange equations become when we write them out, knowing that there is a potential involved. So remember the Lagrange equations, we all know them. Qi plus del T by del Qi is equal to d by dt del T by del Q dot. Well, Qi can simply be replaced. Nothing wrong there. Qi is minus del U by del Qi. And Qi approximate, like that is reference. So I can write this out as minus del U by del Q plus del T by del Q is equal to d by dt of del T by del Q dot. Well, I can kind of group everything here. This is all differentiated with respect to the same variable. So I can take out a del by del Qi and see what's inside. It's T minus U. And on this side, I have the same thing. T del T del T. That's all very nice, but I in fact want to make one more step. I want to observe what I said in the beginning, in the very beginning of this whole discourse. I said potential energy in the case of conservative forces, not monogenic, potential energy is dependent only on position, not on velocity, correct? Okay, let me get rid of this now. If potential energy is position dependent only, then we expect that when we differentiate it with respect to a velocity, a dot, right, it should be 0. Right? Only a function of position. So, using that, I'm going to try and write this in a more symmetric way. If this is true, right? Then I can write del by del Qi dot of T minus U, if I like, right? Differentiation is a linear operator. That's just the derivative of T minus the derivative of U. But the derivative of U, as we've just shown, is 0. So this is just del T by del Q. Okay. No black magic going on. What we've done is we've noticed that U is independent of velocity, and therefore I can take the derivative and it gives me right. So let me substitute this relationship back into here. All I'm trying to do is get things in a more symmetric way. So certainly there's nothing wrong with this equation, it's correct. But I'm trying to kind of follow mathematical beauty to get a more symmetric looking. So I've got a del T by del Qi dot here, and I've got a del T by del Qi dot here. So I can replace this one with that. Okay, let's do that.